Dr. Rachel Winston for the next edition of the Mathematics video series on applications of geometry. Shape and form define our universe, from the basic shape of our planet and the plants, trees, mountains, coastlines, to the animal kingdom. Astronomers look into space to understand shapes of planets, galaxies, and various cosmic objects. From the dawn of civilization, people have been curious about geometry, a term that comes from the Greek roots geo, meaning earth, and metria, meaning measure. We will venture back thousands of years to the roots of mathematics, where geometry was born. People needed to count and estimate distances. Measurement of shapes for buildings, like the Great Pyramid of Giza, built in Egypt about 2500 BC, is unfathomable without significant understanding of geometry. For 3,800 years, the Great Pyramid of Giza was the tallest man-made structure on the planet. In every early civilization, there are examples of geometric discovery. The geometry of early civilization was focused on construction, trade, security, and astronomy. All of these areas required accurate measurement, particularly to determine building heights, paths of projectiles, geometric distances for travel, and the movement of planets. Mathematicians served as advisors to government leaders to provide the calculations that could build, maintain, and protect their region. Archimedes was known for his ability to use geometry to protect Sicily against the Roman army. Thales is considered the first to present geometric proofs. Shortly afterwards came Pythagoras, known for the Pythagorean theorem, a way to determine the lengths of the sides of a right triangle. Actually, Pythagoras was not the first to consider the Pythagorean theorem, but he traveled extensively, brought back many ideas, and extended the concept and uses of the theorem. Euclid codified geometry in 13 books, called the Elements, which is the most widely read book in all of history next to the Bible. Numerous architects, astronomers, artists, and scientists extended geometry over hundreds of years. However, most students have drawn a graph on a Cartesian coordinate system, which is a convenient way to visualize mathematics, created by René Descartes. Today, what started as points on a Euclidean plane has been extended to 3- and 4-dimensional ideas. Pixels that allow us to see images on a television screen, computer graphics, and virtual worlds. Today, rather than locating every point to display an image, computer graphic developers use fractals, a mathematical concept that replicates self-similar patterns and repeating patterns. Although the beginnings of the idea of fractals is traced back to 17th century mathematics of recursion, the term fractal was first coined and developed by Benoit Mandelbrot. This concept has been used throughout computer-based modeling to geometric patterns of nature that can explain the growth of plants, patterns of time, and scores of images, sounds, and natural occurrences. While the mathematics is complex, the idea is not. Furthermore, understanding fractals can help you better understand images, animation, film, and computer simulations we see throughout our life. Fractal art, like these images, demonstrate the self-similarity concept. By rotating the image and zooming in on a specific part, you can see that the image replicates itself. If you zoom even closer, you can see previously invisible forms of the same shape and form. However, one of the most fascinating aspects of fractals is the possibility that computer graphics, mathematics, science, and art can come together to explain growth, transformation of mountains, coastlines, clouds, rivers, sound patterns, and electrochemistry. Looking closely at a fern, you can see self-similarity, but models of many naturally occurring branching patterns can be created. What the mathematics allows us to do is to create a model like the regularly occurring form in nature and have that model predict what may happen in the future or create an unexpected outcome. The mathematics of fractals continues to grow. Another geometry that is being developed more in this century is topology. This area, first termed topology by Johann Benedict Listing in the 19th century, studies shapes and spaces incorporating stretching and bending. However, the idea of topological spaces was extended in the 20th century. We don't hear much about this in everyday life, but this subject also allows us to visualize, understand, and model real-life patterns of nature. The field of topology will continue to grow as computer-aided graphics becomes more developed. Let's look at a figure like a sphere that has a genus of 0, because there's no hole of any type. Squishing it or stretching it still leaves it with no hole, although deformed from its original shape. Now let's look at a Mobius strip that has a genus of 1, or a donut that has a genus of 1. Notice that the donut can become a coffee cup through reshaping. Anyone who has played with Play-Doh or silly putty has manipulated the blob into something using topology. Now imagine a blood cell flattened or reshaped, or imagine a human body squeezing through a small space. Our bodies reshape. We can use this to create the robots of the future that are not metal and hard, but soft and topologically equivalent. This is how computer images may create virtual creatures that are the same but transform, or how biology, physics, astronomy, and computer science, and other fields will use topology. Before we end this video, imagine that you can 3D print a soft, pliable car part that has a manipulatable form, or 3D print red blood cells for transfusion, or that rather than skin grafts from another part of your body, an injury can be repaired by topologically equivalent skin. The animation and video game models of topologically equivalent structures are only limited by the mind's imagination. The world in the future will change significantly, and much of this will be due to innovations in geometry. You may not do the math to create these, but you will benefit from all of those people who improve your life because of this knowledge. That is all for this episode of the Mathematics video series on the topic of applications of geometry. I leave you with this thought attributed to many great thinkers. The only way to predict the future is to create it. This is Dr. Rachel Winston signing out for now.